Hello class, today we're going to be looking at transformations and how we can use a matrix equation to express transformations and apply it to graphs. So let's get into it. So first off, we have a summary of all the different transformations we can apply to a function of x. So we could use any rule here for the function of x, and we can do things like adding k to it, which is a vertical translation. We can operate on the x-coordinate to give horizontal translations and dilations on the y-coordinate and dilations on the x-coordinate. We can do reflections, and of course we can do a reflection over the line y equals x, which is essentially the inverse function. Let's look at the transformations in function notation in a general form. So here's a transformed function of x expressed in a general form with parameters a, b, c, d. So we want to be able to describe what transformation each parameter is responsible for. So first off, parameter a, if it was a negative number, it can be a reflection over the x-axis. Then for a being a number that is other than a 1, so a factor of 2, factor of 3, then it acts as a dilation by a factor of a over the x-axis happening on the y-coordinate. The d parameter over here is your translation, a vertical translation. So if d is negative, then it's a vertical translation by d units in the negative y direction. And if d is positive, it's a vertical translation d units in the positive y direction. So when we're looking at the x-coordinates of the function, the x pronumerals here and everything that's happened to x, one useful way we can rearrange it is take out a common factor of b and express that as another bracket inside the function of x. So we get this now, and we have this plus this factor c divide b, which is added to or subtracted from just the x pronumeral itself. Now we can interpret that now being the horizontal translation in units. So if that fraction is negative, then we translate by that amount c on b units in the positive x direction. Notice how it's opposite. But if that fraction is positive, then it's a translation in the opposite direction, in the negative x direction, by that many units. And that kind of opposite or reciprocal behavior is often found in the equations for the operations on the x pronumeral. So this factor of b here, we're going to describe that as if it's a negative, okay, then we've got a reflection over the y-axis. And of course, if the b is a number other than 1 or minus 1, then it's a dilation by a factor of, have a look, 1 on b, it's that reciprocal behavior from the y-axis. Okay, so that's how we describe all the transformations in general on any function. Let's see if we can apply that to an example. Describing transformation. So here's a transformation that maps the graph of y equals x squared, a parabola, onto another graph. And here's a transformed parabola, and there's a number of things going on. So let's see if we can describe each part. First off, we've got this negative out the front. So that negative there is a reflection over the x-axis. And then we've got the factor of 3 here. That's a dilation by a factor of 3 over the x-axis because it's happening on the y-coordinate. Alright, the next thing is our plus 1, our vertical translation by 1 unit in the positive y direction. Okay, so now looking at the x part, we're going to factorize a common factor of minus 2 from the x we're going to express it like this inside our parabola bracket squared. So that allows us now to identify our horizontal translation. So looking at this minus 2 from the x, that's a horizontal translation by 2 units in the positive x direction. So we've got that opposite direction behavior occurring. Now this factor of minus 2 out the front here, well, the 2 indicates we've got a dilation by a factor of a half from the y-axis. There's that, it's a reciprocal factor. And of course the negative on the x there, it's a reflection over the y-axis. So there, that's how we would describe all the separate unique transformations occurring on our parabola. Let's look at some exam problems. So in this first exam problem, question 1, a transformation that maps the graph of y equals the square root of 8x cubed plus 1 onto the graph of y equals square root of x cubed plus 1. So they're very similar, the 8 is missing. So which transformation is it? So first off, it's good to recognize this here is your original function, whereas this is the transformed function. So it's changed due to some transformation that we need to determine. So because this is the transformed function, we can denote the pronumerals as the y dash and the x dash, just to differentiate it from the original xy coordinates in the original function. So we can see that to achieve this part in the transform function, our original x can be expressed in terms of some factor a multiplied by x prime. And if I substitute that into the original function, then when I apply the power of 3, I'm going to have this 8 times a cubed as an overall factor. Now, this is the structure of the transformed function, which is the same as this. So the coefficient 8a cubed must be the same as 1, because I've got a 1 here as the coefficient of the x cubed term in the transformed function. So what is factor a? It must be a half. So the original x coordinate is equal to a half of the transformed x coordinate. So what is the actual transformation occurring on the original x coordinate to give you the transformed x coordinate? We've got to rearrange to give this. Alright, so how do we interpret this transformation? This is a dilation by a factor of 2 on the x coordinate. So that is part A. That's option A as your answer. Okay, so the point here is rearranging the transformation equation so we can express the transformed coordinate as a rule of the original x coordinate, and the operations then can be the same as the transformations that we can describe. Let's look at the next question. Transformation T, which maps from real numbers in Cartesian coordinates to codomain of real numbers in Cartesian coordinates with this rule. So this is your transformation equation, and that maps the line with x minus 2y equals 3 onto the line with these options. Which one's the correct one? Okay, so by interpreting the description of the question, we have to make a sense that this one here is your original function, whereas these ones are your transformed functions. Okay, so let's apply the matrix equation. Let's do a matrix multiplication and we'll get our transformation linear equations. So x dash is equal to negative x plus 1. Y dash will equal to 2y minus 2. by doing the matrix multiplication and then addition. Now, to apply these transformation equations, we're going to rearrange them. We're going to transpose for the original x and the original y in terms of x dash and x and y dash. And then we can take them and substitute that into the original function. So from the substitution we get this. Now we're going to have to expand and rearrange and simplify, and we come up with this as a simple linear equation. And we can notice, hey, that is the same as option C. Very good. Let's try another one. Question 3. A transformation T given by this matrix equation rule maps the graph of function f to the graph of y equals x squared for real numbers. The rule of f is, okay, so from the interpretation of the sentence, we need to identify that f is actually the original function, whereas y equals x squared, hey, that's the transformed function. So we're going to denote that as with an x dash y dash coordinate. Let's figure out what is the original function. So firstly, if we apply the matrix multiplication, we get our linear equations. Now, to work out the original function, we're going to substitute these guys straight away into the transformed function, because the rules are arranged in a way to make the x dash and the y dash the subject, which is going to replace the x dash and the y dash in the transformed function, and have a rule in terms of the original x and y. So sub it in straight away, and then transpose and solve for y, and we get this as our original function. Option A. Alright, there you go. Question 4. Transformation T that maps the curve with equation y equals sine of x onto the curve with equation y equals 1 minus 3 times sine of 2x plus pi is given by. So now we've got two functions given to us, and we've got to work out, well, what's the transformation? So when we interpret the wording, this is your original function, whereas this is your transformed function. So putting them side by side, we have a transformation T that takes the sine x into this transformed function. So what we're going to do is work backwards. We're going to break down our transformed equation, this one, and rearrange it to identify clearly what are all the operations happening on the y coordinate, and then identify what are the operations happening on the x coordinate. So by subtracting 1 and dividing by -3, it gives us this. Okay, make sure dividing by that negative, you redistribute the negative into both terms in the numerator. So what is this equivalent to? Well, this is another form to show that our y equals sine x transforms into this, where if we match the parts, the y coordinate is equivalent to this in terms of the transformed y, and the x coordinate, x here, is equivalent to this in terms of the transformed x coordinate. So let's express that as separate rules. Here we go. So there's our linear equations. We're going to now rearrange that to get it looking like a matrix equation, but the matrix equation is all in terms of the transformed x and y. So we have to transpose these to get the transformed x and y by themselves. There we go. They're now y dash, x dash are the subjects, but I'm just going to reposition it in this structure. X prime first, y prime second. And by me including these extra terms with zeros on the y and 0 on the x, it allows me the full structure, so I can write that in terms of a matrix equation. There it is. So there's that coefficient matrix, which is the same as these guys in the answers, and we can match that up. So this one actually relates to, that's right, option D. Fantastic. Alright, we're doing very well. Let's look at one more. Question 5. The transformation with this rule maps the curve with equation y equals x cubed to the curve with equation given by this. So, that's your original function, and these guys here must be the transformed function. What we're going to do is perform the matrix multiplication. So we get these linear equations by multiplying this matrix and then adding. To apply these rules, we have to transpose for the original x and original y. So transposing for x and y gives us these equations here. Very good. Now, these now become substitution equations we put into our original y equals x cubed. So, we've got this now. We have to rearrange and solve for y dash. So, multiply by -2. Perform the cube on the quarter. Cancel out any common factors, and the last bit you got to add the 3 to the right hand side, and there it is, our transformed equation. Option A, absolutely. Fantastic. Okay, well, last question, but this time I'm posing this to you guys that I'd like you to be able to do yourself, and do in your exercise books. See how you go. I want you to can you reply or leave a comment down below? Can you tell me what parameters A, B, and C are to apply this transformation equation to this original curve? Y equals 2x squared plus 1. What is the image? What are parameters A, B, and C? Alright, good luck. Keep practicing, work on some exercises, and we'll get better and better.